Hey physics. So this is a big idea slide about the whole forces and acceleration movement or unit that we've been doing. So this is a long unit. There's a lot of stuff in it. So we wanted to make a slideshow that just kind of like talks through all of it. And I'm going to just talk you through that slideshow right now. And yeah, so you can just see again the big summary of what it's all about. All right, so forces. A force is a push or a pull, and every force has both strength and direction. You can find out how much there is and what way it's pushing. So we learned about balanced versus unbalanced forces. So when we have balanced forces, we're working with Newton's first law, which is the law of inertia. Sorry, my kid's cracking up. The law of inertia is what happens when forces are balanced. Things tend to resist a change in motion unless they're acted upon by an unbalanced force, and that leads to acceleration. So there we go. Balanced forces, no movement. Unbalanced forces, there's going to be an acceleration in the direction of the stronger force. Yeah. So here's a list of the forces. We've got gravity, normal force, which is the support force, tension, which is like two sides of a leash. You can feel it on both sides. There's a spring force, which is like that push or pull that you feel when you squish a spring or try to stretch it out. It wants to go back to its normal space. We've got the force of friction, which is rubbing against things. Always works in opposition to the motion of the object. Applied force is just like a push or a pull, and then air resistance is the friction that you have with the air. Yeah. Okay, so then we have system schema and free body diagrams. So remember, system schema are the circly ones with the dashes and the dots to indicate different things, and then a free body diagram is just the object and what forces are acting on it. So some big differences are that the system schema shows you what all the forces are that are acting on it, but a free body diagram, you can tell like the amount of the force and the direction of the force, so you can determine like where things are actually going to move. Some important ways to, like if you're looking at a system schema, here's my advice, is that you look at a couple things first. The object that has a dotted line around it is going to be the object of focus. So yeah, always look for that dotted line and fill in that thing first. So that's going to be like, in this case, like a light bulb hangs suspended from the ceiling. What are the forces acting on the light bulb? And you can like know that this is going to be the light bulb because it's got that dotted line. Then these dashed lines always indicate a non-contact force. So there's three non-contact forces: gravity, the electric force, and magnetism. But like this is always going to be gravity. And then that means that this is always going to be the earth, okay? So again, when we're looking at a free body diagram, the size of the arrows matters and the direction of the arrows matters. And once you've drawn that, you can start calculating net force and determining what kind of motion there's going to be. So this chunk is about adding and subtracting forces when you do each one of those and determining where the motion is going. So when you have a balanced force, it's going to be the same on both sides, or the same up and down, and that means there's going to be no movement. So it's going to be a net force of 0. But if the forces are unbalanced, the net force is going to be not equal to 0. So you can tell that just by looking at the size of different objects. You can also, like, if you add the forces together, so you're either going to add or subtract them. If they're going in the same direction, you add them because those forces are adding on to each other. If they're going in opposite directions, they're canceling each other out. So you're going to subtract that and find out which one is the stronger force. So, yeah, in this case, the net force is 0 because they're pulling with the same amount of force in opposite directions. But in this case, you would add those forces together because these guys are adding their forces together to pull on this guy. And in this case, you're going to subtract again because you will find out that this side has a bit more force than that side. So we always do the largest force minus the smallest force to find out the difference there. Okay, so then you also are going to know about how to relate position, velocity, and acceleration. So to review that, position is where an object is compared to its starting point. And you can think about it moving in actually we're not talking about movement yet, we're just talking about where it is. So where is it in comparison to the starting point? And then velocity is how fast is it getting there? How far can it travel in a certain amount of time? And velocity is important to distinguish from speed because velocity has a direction, right? We know like if they're moving forwards or backwards or to the left or to the right. And for ours purposes, it's just that positive. If it's going one direction, it's going positive. If it's going the other direction, it's going negative on the graph, okay? And then acceleration is a speeding up, a slowing down, or a change of directions. All of those are forms of acceleration because it's moving faster and faster in a certain direction towards that unbalanced force. Yeah. So speeding up, slowing down, or changing directions. Okay, so here is a comprehensive table about all the different things that you need to know about acceleration and graphing, all of this stuff. So if the object is at rest, the velocity is 0, there's no acceleration, and there's no net forces because everything is balanced, and that's why it's not moving. If it's moving at a constant speed, the velocity is not going to be 0. It's either going to be positive or negative, but there's going to be no acceleration because it's not changing speed or direction. And there's going to be no net force because it's moving at a constant speed. So the forces are balanced in that situation. If the object is moving forwards and speeding up, the velocity is going to be positive. You can think about that like it's going to have a positive slope, or it's going to be in the positive quadrant of a velocity time graph. The acceleration is going to be positive, so it's going to look like going to be curving up, and the net force is not 0. You can tell because there is an unbalanced force there, and that's what's causing the acceleration. Moving forwards and slowing down, so anytime there's a deceleration, that means that the forces are working against each other. So we may have a positive velocity, but a negative acceleration, and that would cause it to be moving in a positive direction, but then it kind of like, it's going fast at first and then gets slower and slower. That's what a deceleration is, and that's because the acceleration is going in the opposite direction as the velocity. So if it's moving backwards and speeding up, that's going to be a negative velocity and a negative acceleration, and that's going to cause it to go in the negative direction and go faster and faster in the negative direction as it goes. And then an object moving backwards and slowing down is, again, a deceleration. So those forces are going to be, the velocity is going to be going in one direction, and the acceleration is going in the other direction. So, yeah, that's what causes that. And again, all of those have a net force that's not 0, and that's what's causing the acceleration in the first place. So when this dog is holding totally still, then its velocity is 0, its acceleration is 0, and the net forces acting on it are 0. There are forces going on, right? There's gravity and there's the support force, but they're balanced, and that's why the dog's not moving. So this car with this crazy purple smoke has a constant velocity here, and that means that its velocity is not 0, but it's also not changing, so the acceleration is 0. There's no change in velocity, and the net forces are 0 because they're balanced. It's applying a force to go forward, but the force of friction and air resistance is opposing that at just the right amount so that it's just staying at a constant speed. So yeah, forward, speeding up, forward, slowing down, backwards, this is actually backwards. This should be backwards, speeding up is going to make you go faster and faster, and backwards, slowing down is going to be a negative velocity, positive acceleration. Just fix that real quick. And positive. Okay. So Newton's first law is the law of inertia. So let's think about this law in terms of forces, in terms of velocity, and in terms of acceleration. So an object at rest is going to stay at rest, and an object in motion is going to continue that motion, the same speed and the same direction. That is what inertia is. So now we can say that is all true as long as the forces acting on those objects are balanced, right? A constant velocity, it's going to keep going as long as those forces are balanced. What about in terms of velocity? An object whose velocity is 0 is going to remain at a velocity of 0. And an object whose velocity is not equal to 0 is going to not change. It's going to stay constant if the forces acting on those objects are balanced. But if they're not balanced, then there's going to be an acceleration, right? So that is inertia. And heavier objects always have more inertia. So a bus is always going to have more inertia than a bird, no matter how fast that bird is going and no matter how slow that bus is going. There's always going to be more inertia with the larger object. Newton's second law is talking about unbalanced forces. So mass in motion, force in motion, and that equation that says force equals mass times acceleration. So the more force, so force and acceleration have a direct relationship. The more force you push something with, the faster it's going to go. But mass and acceleration have an inverse relationship. The heavier something is, the more you're going to have to push to make it go. But if you apply that same force to a heavier object, and it's not going to move as fast, right? And you can feel that in your body. That's just like if you are trying to move something heavy with the same amount of force as something that's lighter, it's just not going to move as far. And we can talk about this phenomena in terms of an equation, and that equation is force equals mass times acceleration. And here's this handy-dandy triangle. You cover up one of those things and you can figure out, you do the operation that is shown here. So if I want to find force, I do mass times acceleration. Mass is force divided by acceleration, and acceleration is force divided by mass. Position versus time graphs. Okay, so first thing you want to do when you're looking at a position, well, at a graph in general, is figure out what is on the y and the x coordinates, position or velocity. So if you're looking at a position time graph, the first thing you want to do is to figure out the velocity. How is the velocity changing over time? And to do that, you're looking at the slope of that graph. Is it going forwards, or is it going backwards, or is it holding still, or is it moving at a constant velocity? What's it doing? And then from there, you can figure out, is there any acceleration? Is it going faster or slower at a constant rate? So this object is moving forward at a constant rate. This object is moving backwards at a constant rate. And I can tell because those lines are straight. This object is accelerating because as time goes by, it's covering more and more distance every second. So this is kind of what your cart on an incline lab looked like. This one is going faster and faster in the negative direction. So this is a negative acceleration in the negative direction. These are both decelerations. They are starting off at a really steep slope, and as time goes by, they're covering less and less distance as the seconds go by. So this is deceleration in a positive direction, or positive velocity with negative acceleration, moving less and less meters every second. And this is deceleration in the negative direction. So this is a negative velocity with a positive acceleration, meaning that that's the tricky one to like think through like logically, but that one's like basically the forces are working against each other, right? You're going in this direction, but the acceleration is kind of pushing your curve up like that. That's how I like to think about that one. Okay, I've got 50 seconds left. Yeah, if you want to check these lines out again too, you're totally welcome to. That's another good way to look at this stuff in terms of a velocity time graph. Okay, so I hope this was helpful, and good luck on the test on Friday and Monday. Okay, bye.